probably there will be some common themes with Stefani's keynote about dependent types from Wednesday. So, as you probably all know, GHC offers a lot of support for type-level programming. We have all these extensions like functional dependencies and gadgets and open type families that have been around for several years. We have data kinds and kind polymorphism that were added to GHC 7.4 2 years ago. We have type-level literals that made it into GHC 7.6 and were further improved in GHC 7.8. And we have closed type families added to GHC 7.8 this year. And with all these extensions, type-level programming in GHC is becoming more and more expressive. And the question that I and Richard asked ourselves in this research was, are we there yet? That is the type-level programming in GHC as expressive as we would like it to be? Or, in other words, can we express all constructs that are available at the term level also in the type-level language? Now, if you think about it for a moment, you will quickly realize that there are a lot of features, language features at the term level that are not available in types. I mean, look at the list, right? And so these are missing from the type-level language, and yet in our research we have found out that the answer to our question of are we there yet is almost. That is, almost all these constructs can be effectively encoded in type-level language available in GHC today. There are some features that work partially and some that don't work at all, and this will be also discussed later in the presentation. So our major contribution here is identifying a subset of term language that can be encoded in the type-level language that we have available today. And you probably remember from Stefani's keynote that there was some work already done in this direction, most notably Adam Gundry's work on also on identifying the shared subsets between terms and types in Haskell. The differences are that Adam Gundry's work reformulates core, whereas our work does not. We build only on existing features. We don't add anything new to GHC. And also, Adam Gundry's formulation excluded partial application from this short subset, whereas we have found a way to encode partial application at the type level in GHC. So, well, all in all, this is just yet another step towards dependently typed Haskell, because in dependent types you want to write your functions at the term level and then want to be able to apply them to types. And this is what we did. We wanted to provide programmers with access to convenient type-level programming by allowing people to write term-level definitions and then have those definitions promoted to types, that is converted to type families. Our solution is currently implemented in template Haskell. It is part of Singleton's library. You might be familiar with Singletons because this was subject of Richard's talk 2 years ago here on Haskell Symposium. And we want our work to be an exploration of a design space for possible future GHC extensions. Okay, so let's look at key ideas behind our promotion algorithms. We rely on two concepts. First of all, we use lambda lifting to promote things like case expression, let statements, and lambdas. And then we use the functionalization to get partial application and first-class functions at type level. And as you can see from the references I've inserted in this slide, neither of this concept is a new one. I mean, both have been around for a couple of decades. So let's look at lambda lifting first. So whenever we encounter, for example, a case expression, we turn it into a type family. So we float it up to the top level. That's why we say we're doing the lifting. And the only tricky part here is that the case expression might be using some bindings that are visible in scope, which basically means that we need to convert all the in-scope bindings into explicit parameters to a type family. So this is best explained by an example. Here's a from maybe function taken from the data maybe module. And the body of the function is just a case expression. And if we convert it to a type family, we will get something like this. That is, that body of a type family will consist of a single call to a case expression, and you can see then that D and X arguments are passed into the type family because these are the bindings that are visible in scope. And then the last parameter is the scrutiny. In this case, this is also X. And the type family that implements the case expression looks like this. It basically does pattern matching on arguments and then returns the result accordingly. And this is all about lambda lifting. Let's talk about the functionalization. And as you will see, the functionalization, the encoding introduced by functionalization will be a bit tedious to use. So before going into any details, I want to justify why do we even need the functionalization. That is, why can't we just have partially applied type families in GHC? So the thing is that GHC's type inference relies on these two assumptions to perform type decomposition. First assumption is injectivity, which says that if AB unifies with AC, then this implies that that B must unify with C. The other assumption, which we call generativity, says that if AB is to unify with CD, then this implies that A must unify with C. And both of these assumptions are true for type constructors, but neither of these assumptions is true for type families. And if we allow type variables to unify with unsaturated type families, then this would be incompatible with these assumptions, and the functionalization is a technique that allows us to work around that limitation. Let's introduce the functionalization by looking at an example. Here's a data type of natural numbers and a predecessor function. At the term level, we are allowed to use pred in an unsaturated way. For example, we can pass it as an argument to map function. So let's look at how this might look at the type level. So promotion of pred function is pretty straightforward, just two equations, pattern matching, nothing difficult here. And the problem is that it is invalid to write something like this. We are not allowed to write pred as an argument to a hypothetical map function, because pred is an unsaturated type family and we are not allowed to do that. So what we will write instead is this. Pred sim, sim standing for symbol, will be something, a first class type level value that can be passed around at the type level. So what can it be? Well, types can be passed around at the type level in GHC, that's allowed. So we will declare the symbol to be an empty data type. And the important thing about this data type, about this symbol, is the kind that we assign it. We assign it with a kind net, double arrow net. The double arrow will be a kind of type level functions that are neither injective nor generative. And in this case, we say that the pred symbol is a function from natural numbers to natural numbers. I don't present the encoding for double arrow because it's pretty obscure. It's easier to use this notation here in the slides. And because we've assigned the symbol with this double arrow kind, we've lost the ability to apply it, because we can only apply things that use the normal arrow. So we must recover that ability by defining the application operator, that double apply sign, which will allow us to apply symbols to arguments. And in the case of pred symbol, we want this property to hold. We want to be able to apply pred symbol to an argument, and once we do that, we want to call the original pred type family. Okay. So what's the exact nature of the apply operator? We declare it to be an open type family, which takes two arguments. It takes a symbol of kind k1 double arrow k2 and an argument of k1, and it obviously returns the k2, the argument of kind k2. In other words, we can view this type family as a function that takes symbols and turns them into functions that GHC can actually apply. Okay, so this is the functionalization, that is turning functions into symbols and then creating a function which interprets the symbols, that is allows to apply the symbols to arguments. And this encoding is, well, it will be a bit burdensome if you were required to write all of this by hand. And I promised you a way of writing your terminal code and getting all of this for free, so I keep my promise. Here is the pred function once again written at the term level. And all you need to do with our singletons library, you just wrap this definition into a call to promote, and the promote function will generate the type family pred, it will generate all of the functionalization symbols, and it will generate the instances of apply function for these symbols. And Dominic yesterday complained about having to maintain separate definitions of knob at the term level and at the type level. So Dominic can write something like this. He can take the knob function and promote it, assuming he has already promoted the ln function, which we are using here. Okay, so you get all of this generated for you, the definitions, symbols, apply instances, and so on. But the problem is that you are still required to learn how to use the symbols. You are required to learn how to follow our naming conventions. You need to write the symbol names explicitly, and so on. That's a bit difficult. So now that I have shown you how the functionalization works, the important question is, could we actually avoid the functionalization? Could we just get away with it? And I and Richard believe that the answer to this question is yes. We could avoid the functionalization. That is, we have used these symbols because we had to, because GHC wouldn't allow us to write partially applied families, so we've constructed this workaround. But the important thing is that once this workaround is in place, once we have it, it actually works. That is, it is not incompatible with GHC's type inference assumptions, right? We have partially applied type families, and GHC's type inference didn't break. So what we believe is that it is possible to have all of this encoding, all of this explicit encoding, go under the hood in GHC. And the only things that would be exposed to the programmer would be this new kind of type families, because we need a new kind, because type families are neither generative nor injective, and the apply operator. So here's a hypothetical map function, and we apply f to x using this new apply operator, because f is a type family, possibly a type family. It is not injective, it is not generative, and it would be wrong for GHC to attempt to decompose this application, to try to apply, for example, injectivity. The questionable part is the second one, the one in the blue color. Here, it's possible that GHC would be able to infer that apply operator is not necessary, because we are explicitly using a type family, so we are applying a type family, not a type variable. Okay, I promised to tell something about the unpromotable language features, so let's have a look at them. Haskell is a lazy language. It allows to have infinite terms, but it doesn't allow to have infinite types. So if you write the iterate function, which generates an infinite term, and then you promote it, everything will work. And when you attempt to use the iterate function, everything will break, because you will get an infinite type error. And obviously, if infinite terms don't work, then also arithmetic sequences which generate infinite terms also don't work. But arithmetic sequences that go from, for example, 1 to 3 are perfectly fine. Our support for literals relies completely on GHC's built-in support for literals, and we found that to be problematic and limiting. The trouble is that currently there's a significant mismatch between what we see in terms and what we see in types. So, for example, numbers. So at the term level, we have 3, which is num a, arrow a, which is a polymorphic literal. And this, for example, can be an integer. Whereas at the type level, we just have natural numbers. But the problem is when it comes to negative numbers, because integers can be negative, whereas natural numbers obviously cannot. Similar problems are encountered with strings, because at the term level, strings are a list of characters, and they can be decomposed. Each character can be inspected, whereas at the type level, string literals are atomic. They cannot be decomposed, so any term level function that decomposes strings, inspects the single characters, will fail to promote. And obviously, if we have such problems with strings, then show and read type classes that require manipulation of strings will also not work. I haven't spoke about promotion of type classes here, but we do promote type classes. So do notation is a syntactic sugar for returns and binds, and both these operators require higher kinded types, and if we wanted to promote this one level up, we would need higher sorted kinds. We don't have that in GHC, so we cannot promote the denotation. Well, and obviously, list comprehensions that are a syntactic sugar for the denotation also do not promote. Okay, so what are your next steps? So first of all, you can cable install singletons to get the library. You can go to GitHub, you can read the documentation online, you can get involved in the source code, and if you find a way to break our library, which I don't doubt you will find a way to break it, please report it as a bug. And you can read the paper to learn more. For example, about the fact that we have promoted Prelude and several of the data modules. So in fact, you don't need to reinvent the wheel. You don't, Dominic doesn't have to promote the nap function. He can just import it from the already promoted modules. We discussed promotion of type classes and instances. We even promote automatically derived instances. So if you write a data type and you derive an ORD instance for it, for example, and then wrap all of this into promote, then we will derive the promoted ORD instances. There's also a formal proof of our algorithm, some discussion of kind inference, and a couple of other things. And so, most of all, you can start doing dependently typed Haskell today with things that Stefani showed in her keynote, with our support for simpler writing of type level functions. This should be easier, and we want you to share your independently typed programs in Haskell. So if you have anything interesting, you can. So Stefani has a repo at GitHub. You can send pull requests to her, or you can blog about it. Send us links by emails. Just share your dependently typed code. Okay, and this is all. Thank you.
Okay, we have time for questions.
Hi. First of all, I'd like to thank you, and this is incredibly impressive, especially lifting, especially the partial type applications. This is just mind-blowing. But my question is, when we start lifting everything to type level, right? So you're talking about classes on the type level, and then we presumably would need some enhancements to the kind system, and then maybe we'll want classes on the kind level. So do you think this will ever end, or do you think like 3 levels is enough?
Well, it's difficult for me to say this because, well, you have like fully fledged dependently typed languages like Agda, where the whole hierarchy of universes doesn't end, right? You have set 1, set 2, set 3, and so on. Whether this will happen in Haskell, honestly, I doubt. I think that, I hope that one day we will get higher sorted kinds, we will get higher sorts, and well, who knows, perhaps somebody comes up with an application which requires going up 1 level, maybe. Perhaps this will be a motivation to further improve things, I don't know.
Any other questions?
Maybe I'll just make a quick response that Richard and Stephanie are busy implementing star in star, so then rather than having a whole hierarchy of type levels, it just sort of collapses. So yes, it'll stop, right? And you'll get many sorted kinds, right? So there you go, we're done, nearly. When Richard's finished, get on with it, Richard.
So something that's not clear to me is, I mean, you're taking Haskell code and putting it in the type level. Wouldn't it be easier to just have a Haskell interpreter in the type checker and just use Haskell?
Well, if you form a question that way, then my answer is yes, it would be easier. Just we don't have that.
Termination. What about termination?
Well, they have non-terminating type functions and they just break, so I guess different ways of breaking things, that's okay.
I can tell you why this is not right.
So you mentioned that it's, well, or you said it's currently implemented in template Haskell. What do you mean with the currently? Is the plan, you mentioned GHC extension, is the plan to turn it into something else?
So there are no concrete plans at the moment. We hope that perhaps if this experiment turns out to be successful, then one day this could be made part of GHC. So as I said in the beginning, this is an exploration of possible design space. Perhaps somebody comes up with something that works better, or is, I don't know, simpler to implement. So we're just exploring what is possible to do. So currently we just have the library. In a couple of years, if this is successful, perhaps this will be in GHC.
So I'll ask that question. So are they terminating your lifted up things?
Are they terminating?
Yeah, so the type families that you end up with.
Well, if they don't terminate at the term level, they don't terminate at the type level.
Okay, so that's using the undecidable instances.
No, it's not using undecidable instances.
Okay. I think. Okay. Well, okay. There's usually quite. I mean, the normal constraint on type families stops you doing lots of, well, forces you to have sort of monotonically decreasing reductions and things like this. And, so usually you get stopped from doing these things unless you turn on undecidable instances.
Well, I mean, you can write things that will, for example, the iterate function, right? You can promote the function, and when you try to use it, it breaks because it causes, it creates infinite type, right? So this will break. So you can write code that will promote correctly, seemingly, but is unusable.
Okay, but for the finite types, I can should be okay. I think maybe.
I think it still would be possible to write code that will break, meaning that has a finite type and still for some reason doesn't work. I think.
Yeah, I think usually it would just be a type error though, rather than actually diverging at the type checking time. But I'll have a play and we'll have a look.
Okay, so I understand that this is mainly experimental, but still, what's the largest program that you've actually written using the singletons library so far? And can you say anything about the implications for compile time efficiency?
Okay, so the biggest program, the biggest promoted set of functions that we have promoted were the modules from the base. These were the data list was the biggest one. Probably it was I don't remember tens of functions. So compile time efficiency could be better. It's not a disaster, but you come to a point where you start to notice that this is happening behind the scene, and it sort of slows down a bit your
right. I'm more interested in sort of the qualitative correspondence, not so much. I mean, you're using, for instance, this lambda lifting technique. So if my normal term level function would run on a certain complexity class, do I have any kind of guarantee that the type level function will be in the same complexity class?
My speculative answer would be that in this case, yes, although all of this encoding actually adds some extra overhead, right? Mm-hmm. This is expected, but I think that so complexity should be preserved.
I would say to be a constant factor, but a very large constant factor.
Right. So, well, my impression is that I sometimes get exponential behavior in places where I don't expect it. So that's basically what I'm asking. But I mean,
you're saying with singletons?
Well, not specifically with singletons. When doing type-level programming on GHC.
I mean, if you discover something like this happening, for example, with singletons, then please do report to us. We will investigate what happens.
If you discover it anywhere else, then please do report it.
Okay, one last question.
So, actually, it's more of an observation on the previous question, which is that, I mean, so I think probably you would find quite big differences because there are completely different operational semantics for what's going on at the type level and what's going on at the term level. I mean, one of the things being the type level is effectively strict rather than lazy. And I wonder whether you sort of have any insights into how we might sort of reconcile the differences between the operational semantics.
Okay, I think this is the area where I don't feel very confident, but I remember that at some point we have taken the backward state monet from one of Philip Wadler's papers, which is supposed to work only with lazy semantics and impossible to work with strict semantics, and it promoted. That is, it worked with the bind function worked with after promoting at the type level, so it wasn't that strict. I mean, the GHC was still able to solve the constraints.
Thank you.
Okay, I thank Jan once again.